So the second type of chemical analysis that we're going to look at is a combustion analysis. So in a combustion analysis, what we do is we take a compound and we burn it, and then we analyze the mass of the products that we get, and then we're going to kind of like work backwards and figure out what the formula of that substance is. So we have an unknown, and we burn it, we react it with oxygen, and we make some products. And we measure the mass of all of the products that are formed, and then we kind of like work backwards and figure out what the unknown is. Now, what's important here is that combustion is an example of a redox reaction. We can kind of tell that because any reaction that involves an element is always a redox reaction. So we're using what we've learned about redox reactions and giving it a really practical purpose. Okay, so a common class of compounds that we'll often apply combustion analysis to are hydrocarbons. And the reason that we can do this is because the products are really predictable. Whenever we take a compound that is composed only of carbon and hydrogen, that's what we mean by a hydrocarbon, and we burn it, we only ever obtain two products, that is carbon dioxide and water. So this makes these guys, a really good target for combustion analysis. So how typically the combustion analysis of a hydrocarbon will proceed is that we'll burn our sample in a large amount of O2. So like way more O2 than what we actually need to ensure that our sample gets completely burnt up. And typically what we'll do is we'll put our sample in a furnace, we'll heat it up a lot, and then we'll blast it with a stream of O2. And that'll ensure that combustion occurs, but also what it'll do is it'll move these gaseous products of the reaction along. And then what we'll do is in a second compartment, we'll have a dish sitting on a balance. And in that dish is a substance, and a good example of this is magnesium perchlorate, that absorbs water. And what will happen is the water will get absorbed out of the mixture of gases that's coming from our, from our sample chamber, and we'll be able to weigh. The water will get absorbed, and we'll be able to weigh how much water gets absorbed. So we get a direct amount of water in grams. So after the water's been absorbed, we'll blast that the gases on into another chamber, and in that chamber we have a similar setup of a dish sitting on a balance, but in this dish is a substance such as sodium hydroxide that absorbs carbon dioxide. And as the carbon dioxide is absorbed, we'll be able to determine the grams of carbon dioxide that were produced in our reaction. So in this sort of three-chamber setup, what we can do is burn a known amount of a hydrocarbon and then figure out how many grams of water were produced and how many grams of carbon dioxide were produced. And we're going to work backwards and get the formula for our unknown hydrocarbon. So yeah, that's basically what's going to happen. Now, there are only a few things to be aware of here. Is our compound contains only carbon and hydrogen, so we can see pretty clearly that the number of moles of CO2 that we get is just going to be equal to the number of moles of carbon that were in our compound, and perhaps this is less obvious. The number of moles of hydrogen that are in our compound is only 1/2 the number of moles of water that we produce. So typically this is going to be the general form of a combustion reaction for a hydrocarbon. So we have this hydrocarbon, it's got A moles of carbon in it, and it's got B moles of hydrogen in it. And this will form A moles of CO2 when it is burnt, and 1/2 B moles of water, right? And we have to have 1/2 of the B moles of water because we have 2 hydrogen atoms for every 1 mole of every 1 water molecule. So what we're going to learn how to do, what the combustion analysis is going to allow us to do, is to figure out the empirical formula of a hydrocarbon. So it's a pretty simple process. All we have to do is figure out how many moles of carbon do we make, how many moles of water do we make, how many moles of hydrogen are contained in that water, and then compare the ratio of moles of carbon to moles of hydrogen. And from there, we're going to get the simplest whole number ratio of those two elements. So here's a good example, right? Combustion of a hydrocarbon results in the formation of 1.320 grams of carbon dioxide and 0.54 grams of water. And then we were asked, what is the empirical formula of the compound? So we're just going to remind ourselves of the general equation for the combustion of a hydrocarbon, and we see that we get 1 mole of CO2 for every mole of carbon that's in our compound, and we get half a mole of water for every mole of hydrogen in our compound. So the first thing I'm going to do is calculate the number of moles of each of the two products, i.e. the CO2 and the water. So how do I do that? Well, I just take the mass in grams and multiply that by 1 on the molar mass. You'll probably remember pretty quickly that the molar mass for CO2 is 44.01 grams per 1 mole, and the molar mass for water is 18.02 grams per 1 mole. I doubt you're going to be calculating these every time. So how much have I got here? 1.32 times by 1 on 44.01 gives me 3 by 10 to the minus 2 moles of CO2 in this case, and then I'm going to do the same with the water. 0.54 grams of water times by 1 on 18.02, and sure enough, I got 3 by 10 to the minus 2 moles of water. So I don't want the moles of water, I want the moles of carbon and the moles of hydrogen atoms. So that's what I'm going to do here, calculate the moles of carbon and hydrogen in the sample. It's pretty simple, right? Because I get 1 mole of CO2 for every 1 mole of carbon in my compound. So that one becomes, you don't really have to do anything for that one, right? The moles of CO2 is exactly equal to the moles of carbon in the sample. But I do have to remember that for the water, the moles of hydrogen will be twice that value. So I had 3 by 10 to the minus 2 moles of water molecules, and I have to remember that there is 2 moles of hydrogen for every 1 mole of water. And this thing here is forgotten all the time. So in my compound, I have 6 by 10 to the minus 2 moles of hydrogen. So most of you guys could probably see the ratio at this point. For every 1 mole of carbon, I clearly have 2 moles of hydrogen. But if you can't, what you want to do is identify the smallest number of these two. So in this case, it is the moles of carbon, and divide each of your moles by that smaller value. And then that'll give you the coefficients that go in your formula. Now, sometimes it does, and you have to multiply through by a small whole number to get a whole number ratio. But most of the time, this one will do it. Just divide by the smaller value to get your A and B that go into your formula. So there we are. We figured it out that the empirical formula is CH2. So here's another one that is much more elaborate but uses the same kind of principles. And the reason why it's much more elaborate is because we have a third element. It's pretty rare that you get one that has a third element, but we're going to run through this calculation and show you how it's done. So the compound eugenol contains both carbon, hydrogen, and oxygen. And we're told, so it has this kind of generic formula, right? CaHbOc, and we're going to be trying to figure out what A, B, and C are. It says combustion of 21.8 milligrams of eugenol yields, and then they give you the amount of CO2 and the amount of H2O, and then you're asked what is the empirical formula of eugenol. So the first thing I'm going to do is calculate the number of moles of carbon that are in my sample of eugenol and the number of moles of hydrogen atoms that are in my sample of eugenol. And I'm going to use the same steps as before. Once I've got those numbers of moles, what I'm then able to do is turn those into masses and subtract away from my total mass, and you guessed it, that's going to give me my mass of oxygen. So first step, I'm going to calculate the number of moles of CO2 and water that are produced. And then my next step will be to turn those moles into amounts of hydrogen and carbon atoms in my sample. So now what I'm going to do is calculate the moles of carbon and hydrogen in my sample. So that's pretty easy because for the carbon, because I get 1 mole of carbon for every 1 mole of CO2, so I don't really need to do anything. But for my hydrogen, I've got to remember that I get 2 moles of hydrogen for every 1 mole of water. So there we go, we've got it. Now, if the compound was a hydrocarbon, at this point, I'd be almost done. I'd just have to try and figure out the ratio of carbon to hydrogen. But I'm not done. What I got to do now is figure out how many moles of oxygen are in my sample. And I told you that the technique that I'm going to do here is to use the difference. So I'm going to calculate the mass of carbon in my sample and also the mass of hydrogen in my sample. And I'm going to subtract those two numbers away from the total mass. And what will that give me? That'll give me the mass of oxygen in my sample. So we're going to do that now. So I'm going to calculate the mass of carbon and hydrogen in my sample, subtract that away from the total, and that'll lead me to the mass of oxygen in my sample. So here we go. I'm going to calculate the mass of carbon by taking the moles of carbon and multiplying it by the molar mass of carbon. And then I'm going to calculate the mass of hydrogen by taking my moles of hydrogen and multiplying it by the molar mass of hydrogen. So there are my two masses there. What I'm going to do now to get the mass of oxygen is take the total mass of the compound and subtract away everything that's not oxygen. So when I do that, I get my grams of oxygen that are in my sample. And sure enough, I can turn that into the moles of oxygen that are in my sample by multiplying by 1 on the molar mass of oxygen. So I do that and I get my moles of oxygen. All right, so now I have everything. I have my moles of carbon in my sample, my moles of hydrogen in my sample, and my moles of oxygen in my sample. I can go ahead and try and figure out the ratio between those two things, or between those three things, and get the formula. So this is what I know. I know the moles of carbon in my sample, I know the moles of hydrogen in my sample, and I know the moles of oxygen. So what I'm going to do is identify the smallest of these numbers. It's got to be this guy here, and I'm going to divide all three of them by that number, right? So, and then that'll give me my coefficients that go in my formula. So my coefficient for my carbon is going to be my moles of carbon divided by my moles of oxygen. And there it is, and that gives me that I have 5 carbons. Then I'm going to do the same for hydrogen, and I'm going to put my moles of hydrogen, divide that by my moles of oxygen, and sure enough, I get 6 hydrogens. And then finally, I'm going to figure out my coefficient for my oxygen. So I take my moles of oxygen, divided by my moles of oxygen, and obviously that gives me a 1, all right? So there I go, I got my empirical formula. So combustion analysis for just the hydrocarbon, pretty straightforward. But if you have a third element, could be oxygen, could be any third element, let's just call it X, right? It gets significantly more complex, and you sure as heck would want to be practicing those before you're having to try and deal with one in a test or a quiz. Okay, so the thing that we know about the empirical formula is it could be the same as the molecular formula, but it might not be the same as the molecular formula. So always be really, really, really careful as to whether the question is asking for the empirical formula or the molecular formula, and hopefully you recall how to convert from the empirical formula into the molecular formula if that's asked of you. So just keeping that in mind, I'll just say this quickly now. So we were C5H6O1, C5H6O1. the molecular formula will be a whole number multiple of that. So n could be 1, 2, 3, etc., etc. And how we can tell whether the molecular formula and the empirical formula are the same is because the empirical formula mass will equal the molecular formula mass. So if the molecular formula mass equals the empirical formula mass, then you know that the empirical formula and the molecular formula are the same. If they don't equal, if the empirical formula mass is less than the molecular formula mass, then you have to multiply your empirical formula by a whole number until those two are equal. Okay, so that concludes the video for combustion analysis. You just need to practice some problems. They all tend to be done the same way, and yeah, have fun with this.